Welcome, I'm Bill Wake. Today we're wrapping up a project. It's an interpreter and compiler for a Forth-like language, and lately we've been doing a Hangman game to demonstrate that it works, and we got a little bit of work to do there, and then we're going to poke around a little bit in the implementation and do a little summary and wrap up. All right, and then I'm off after today this week. I'll be back next week, Thursday. Okay, so let's just do a make sure our tests are all good. That ran fast. Wonder what's different. Okay, everything's green. Good, good, good. All right, let's take a look. Well, our Hangman, we are in the middle of doing the body parts. That's really the last major piece to do. And we were trying to extract a common draw routine. And we did extract it, except it didn't work very well. So let's try that again. All right, so Hangman. I guess I gotta look for the words redo. There we go. Okay, so here's draw head, and it basically has to save the draw routine, figure out what row and column to draw on. So it updates the column in this case because the row starts out right, and what character to draw. And then we make sure that the draw routine gets called. Okay. Draw torso, that one's kind of different because it draws two characters, the upper and lower body. And we could have cheated, not exactly cheated, but we could have taken an easier way out and done them separate things, but we'll leave that special. And then draw left arm is very similar to the draw body. We save the routine, we adjust the column, we adjust the row. Oh, the row is, no, wait a minute, that can't be right. No, we're adding one to the row and the column. We adjust both. And then we save that string and then BCA and draw. Okay, so in a sense, it's clear what to do, but the problem is we need more information. So I think, well, all right. So what we were headed towards is we need column offset and row offset as well as the other stuff. And I don't know, the order of this maybe not as helpful. Column and row is what comes in to each routine because it's where the bounding box, the upper top left corner cell is at column and row. And then we need to do offsets and updates. Now I think it might be better to, the draw routine we normally save and then it's out of the way. So I think that's good. But the trick is, like, we have to get the column offset. Yeah, yeah, it's tough. Once again we need to save things. Because we can only reach down. Normally, we only reach down 3 levels and 3 entries into the stack. So we have stuff to swap the first 3 entries and all that. But if we've got 3 entries and then we're trying to get to the 4th and the 5th, it's really hard the way we set things up. It's kind of built into the way Forth interprets things. I mean, we could define the methods, that bring out the 4th or 5th element. But I think instead what we'll do is, well, let's peel these 2 off. Yeah, so we'll take the first 2 off and use variables for them, and then we can get things accessed and do that. Okay, so let's make that the goal. Okay, so we're going to come in with this string first. So just like this, I think we're going to, well, I'll take out the redo. Okay, so we want to save this body draw routine into the variable. Okay, so we'll have that later when we call things. Okay. Then we want to save the string. Okay, so let's get our stack right here. Once we've stored the draw routine, we have a string, column, offset, and row. Okay, so let's save the string. Body string, swap, add equals, and that leaves, well, this minus the string. Okay, and now I can see, well, let's just put some space here. Basically, we need to get column offset plus column, and row offset plus row need to be the top two things on the stack, and then we got to swap the string into the third position and manage from there. Okay, so let's work on getting them. They really need to be in the order column, row, string. So I think, well, I'm not sure it really matters. We got the column. Let's bring C to the top. So CAB says bring the third entry forward. So now we have column, call offset, row offset, row. Okay, and if we add, we get column plus column offset and row offset, row. Okay, I guess that's reasonable. Now let's do CBA. Basically flips the top three entries. Any reordering is fine. As well, maybe this is better. We have BCA pushes the top entry to the third slot, which is kind of what we really need. Addition commutes, so we don't really care what order is on the stack. Okay, and then we do another add, and we have row plus row offset, column plus column offset, and we really want column on top and then row. Okay, so maybe I did this backwards. Let's try a different way. All right, so we got column offset. Yeah, there's no good way to get that fourth, to get those done first. I guess we'll live with this. I have to do a swap at the end, but that's not the worst thing in the world. Okay, column offset, row offset. Okay, now we need to bring the string back. Body string at, looks up the string and puts it on the stack. And I switch to this prime once I'm tired of saying what it is. Just that it's different than the original one. It's not any deeper meaning than that. Okay, so we got body string, column, row. Oh, we're close. Okay, we got to do a what's the transformation? We need, I guess it's another BCA. We want the top thing on the bottom. Okay, and now we're kind of down here. This line looks pretty good to me now. Bring back the body routine, get the value, and call it. Okay. Now, nobody's calling this, so we're going to rewrite. Well, let's rewrite draw left arm. I think it's the closest. It uses both a column and a row offset. Okay, so given draw routine column row, oh, well, that does make it I would say that means the string should be first. Well, why does that matter? I guess that makes it slightly easier if the string is first. So let's move these around. Okay, so now the string draw routine. All right, so draw left arm. Well, let's I'm not going to touch it. I'm just going to set it aside. Okay, so we need to call string draw routine. We got column and row, but we need to get column offset and row offset in there. Okay, so let's push. We're given this. All right, so let's push the column offset is, well, they're both 1. That's going to make it a little too easy. 1, 1. And I think that's okay. So now we have column offset. I'm not sure which order they're in, to be honest. Row offset, draw routine, and then let's push the string we want to draw. Oh no, we got to flip these around first. Column, row. Okay, so if we do CAB, we get draw routine, column offset, row offset, column row. Now we add string and all this. Okay, so we have string, draw routine, column offset, row offset, column and row. Okay, so this is column, this is row. Which is okay. It reads better row column to me, and even though the stack is backwards. Okay, but given all those things, now we have everything we need for body draw common. Okay, so we should be able to call that. All right, and then body draw routine. No, we don't want to call that. Oh, change the original. Draw body common. Okay, and that should be empty. All right. Does that seem believable? Row, column, swap them around, put the string on top, and call the common. I think that's about right. Okay, so let's make sure. Do we have a test for left arm? I thought we did, but I get rushed sometimes. Draw left arm. Okay, so we should be able to take this. Notice we got rid of, a ridge is not in the way. Okay, yeah, I'll get there. All right. Paste all that. Make sure there's no red. Okay. And now we'll just take the one test. So draw left arm. Whoops, the test for that one. Okay. We'll just do it all. but we want to call test draw left arm because he's using the common. All right, he seems happy. Yeah, okay. So I would say that's good for that one. So draw left arm is now this. Let's take this comment up here. Oh, I guess maybe this comment. And then we had an array somewhere. Okay, we got draw left arm in there. Good. All right, let's get draw head converted over. So his, well, I guess we want this pattern. His row is offset by 0, but his column is offset by 2. Okay, column, row, draw routine, column, row. Swap it around. And then he draws the O and this. Okay, so let's paste this. And then let's redo his routine. Okay. And let's do hangman. Okay, good. X, Y, Z. All right. A, B, C. Okay. None of those do the job. Okay. But this is good. And so I think I don't feel obligated to manually test all these because I feel like this is very close to being as straightforward as we can want. You know, we've got row offset, put the character in, otherwise it's just the same. They're all the same. So I'm kind of willing to do that. Let's see. Did I delete the wrong one? No, I didn't delete this one. Okay, good. All right. So yeah, we'll verify it manually, but I think once we've seen it draw in the right position once, like there's nothing that makes me think it's going to start blowing up. You know, we got to get those constants right, but that's, you know, that's okay. So with that, I think I'll do the draw right arm, which is going to be very similar. Okay, so the left arm is down a row over 1. The head is at 2, and the right arm is at 3. And the right arm is a backslash. Okay, so let's take draw right arm. Put that here. Then draw left hand. All right, and let's see the picture. So the hand is going to be, well, he's an underscore, so he's going to be in the same row as this and 1 column less than the left arm. Okay, so same row, 0 for the offset. Same row, 0 for the offset, and then his thing is an underscore. Okay, and then draw right hand. Same row. Instead of drawing at 3, we'll draw at 4. Same character. Okay, so now, am I counting wrong? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. All right. And then draw left leg. Well, he's actually closer to the arm. Yeah. Same row, but he's, sorry, no, different row. That's 1, that's 2, that's 3. Row 3, column 1, left leg, okay. Duplicate this one. Okay, draw the left leg at 3, 1. The right leg should be like the right arm, so 3, 3. Whoops. Right leg, 3, 3. Okay. And then left hand will be left foot. And I guess he'll be at 3, 0. Right foot. Left leg. Oops, sorry. You're right. Right leg. Okay, so A, B, C, D, E, F, G, H, I, K, L. All right. Yeah, that's the segmentation fault is if you call this with more than 10, we got 0 through 9, but if you call it 10 or higher, but we're going to address that next. So I think I'm okay with, yeah, I guess I'm okay. There's a limit and we're going to make sure we don't cross it. Okay, so add remaining body parts for Hangman. Okay, and yeah, so I mean, like, There it is. We finally got the whole game. And now we have stuff to do. Okay, so we did these two. Right. Okay. So I want to make the game over. Detect too many guesses. All right. And I think we have a game over routine somewhere. Game over. Okay. So it's checking do you get the right answer? And we want to check, or are you too big? All right. So I think what we have is good. It's a good start. But I think I want to extract this into a method. So I'm going to make a method you win, which is this, is a Boolean. Okay, semicolon. And then let's define it. You win. True if and only if your guesses match the answer, and the input or the function of this is nothing goes to Boolean. And again, we don't really care what the ... is. We don't look at it. We use the variables. Okay. So this should be you win. All right. And so I guess I could test this. It's too easy to make mistakes when you're doing the manual stuff, although I don't think this is going to be a problem. Paste all that and then run our tests. Now our tests definitely rely on game over, so I think they'll show something if there's an issue. Okay, good. Alrighty, and now that was you win. Okay, so well, I'm going to start off. I don't know the term for this. What I do sometimes, I take a structure that's working and then I kind of artificially expand it so it still works. I guess some people call it like nesting or something, but I'm trying to create something that has the same. The tests think it's the same. It acts the same, but the structure is kind of modified to what I want eventually. So I'm going to say there's you lose, and it's supposed to be true if you run out of guesses. Okay, but for now, I'm just going to say it's true. Okay, and then this one is you win, you lose, and then I think we did 2 vertical bars. Oh, we just did 1 vertical bar. Okay, so yeah, so the game is over if you win or you lose, and otherwise you're in this sort of in the middle state. Okay, and since you lose is always true or anything is the same. No, it's false, right? False or anything equals anything. So false or true is true, false or false is false. So yeah, false makes it go. All right, so that vertical bar is not the greatest character there, but this should act the same. And again, since we're replacing the whole thing, I'll just do that. Okay, and let's put the tests in. Test all again. Okay, so, so there you go. That's not the right logic. Okay, yeah, so much for that expensive education. I guess I don't want it, I only want it to be if, wait a minute. If I win, it should be over. If I lose, it should be over. But if I don't win, yeah, I think that's the right logic. I mean, if I don't win and I don't lose, then the game is not over. That seems correct. What did I do? Test empty answer. Did I not? Well, in none, and it goes to Boolean. That much is true. Okay, let's go look at test empty answer. Oh, that test is probably wrong. Well, no. Yeah, something popped too much. Oh, there's lilies. Yeah. Okay. Let's go back here. You win should produce a bool. That's equal dollar. You lose produces a bool. Oh, how about I actually define the function? How did anything work? Oh, I can tell you. It means I missed a red up here. That's tests. Yep. Okay. Grr. And this is why we have tests. Okay. All right. I think that's okay. Let's get those tests in now. Okay, there we go. All right, so this is introduce. I don't know the right word because it's not a fake or a dummy. I don't particularly like that word, but I don't know the right phrase. None. Inactive, I guess I'll call it that. You lose method. Okay. Yeah. But it's not truly inactive. It's just kind of default. Okay, I'm sorry. I need to take a quick break here, maybe 3 minutes. I guess we'll go a little early and then do another one later. Excuse me. All right, welcome back. Okay, let's grow this into the real one. So we need some tests. And well, let's find the game over tests that we have. Okay, empty answer, string answer. All right. I mean, these are kind of calling to string array. Okay. Yeah, I think maybe down here. All right. So test let's say only 9 wrong, hasn't lost yet. All right. And so I think we can oh, this is update wrong guess. Well, I don't know. I'm kind of willing to use the environment we have, that the we have wrong guesses. Let's find that. Okay, must be up here somewhere. Sorry. Okay, yeah. So I'm willing to say we're going to use that, and I'm willing to populate it as part of the test. In a way, yeah. None of the tests use wrong guesses per se, but I'm kind of willing to. I don't know. I'm a little bit reaching inside implementation, but it's kind of like I don't really want to. It's like, do I want to call this every time? I mean, we do look at wrong guesses here. So I'm gonna say that that's part of our interface, is to say wrong guesses is accessible, and so I'm gonna zap it in the first place in one go. Wrong guesses, and then I don't remember how repeat dollar works, but let's go find it. Okay, so repeat dollar, you give it a character, an array, and a length. All right, so we'll push 9 on the stack, wrong guesses, and a character. A. Okay, so it's A, wrong guesses, and 9. Okay, and then we call repeat dollar, and repeat dollar fills the array with 9 copies of A. Okay, so yeah, fill the array. All right, so that's the setup. Then we're going to call game over, and then this should be false. Okay. And this goes empty. This leaves a Boolean, and we assert it. Okay. Yeah, so this test will pass because we have a 0. We always return a 0. Okay. So, I don't know. Do I still have it there? No. We can use it. Basically, it's kind of serving as a boundary case, and it'll pass, or it should pass, if I've understood what I'm doing correctly, which is a good thing. And then this kind of locks down that pass without ever having been wrong. So it's a little unusual for TDD that happens, but it does happen some. Okay. Well, game over. I guess I've got to I think I've got empty strings or something in my clues. Let's do umbrella. Oh, I guess the answer. Umbrella string to array. Yeah. Right. So a test that expects to pass already fails because of setup. It just tells you got to run these things to make sure. Okay. Yeah. So that I think is okay. We've seen it fail for the wrong reason, but it failed, so we know it's being triggered. All right. The real trick is let's do the next one. 10 wrong. Well, let's say game is, well, 10 wrong loses game. Well, no, it's not so much loses, it's makes game over. Okay, so this one is 10, and then this should be 1. Okay, and then I'm gonna, usually I just do one at a time, but I think still has game over. So I think we won't let this happen really, but I think just to kind of bound the way things are working, this is really a count. I'm gonna make the guess, the wrong guess is a little bigger. Okay, so yeah, let me change the answer each time. Arbitrary, unusual. Okay, so yeah, making sure we've both these check for 1. That if we guess 10 times wrong, it should be game over. Does that make sense? Okay, so yeah, we're still with a 0. So let's, I guess we haven't changed those. We can run these now. Now these two should fail because they're doing real TDD. Now writing 2 at once is a little weird, but I think the second one is kind of unnecessary in the way we structure our game. We fail after 10, but I think we'll make sure it's that. Okay. All right. So really, you lose should be looking at guesses, make dollar. No, is it? Yeah, guesses. Wrong guesses. Is that the? Yeah, wrong guesses. Wrong guesses, make dollar, length dollar. Okay, so I guess I can do it like this. $10 and then greater or equal. Okay, so let's do this. Start clean. Bring in at least these 2 tests. Well, let's get all 3. Should pass. Should pass. And this should pass. Yeah, but I think the drawing crashes if we let you answer 10 or more. Well, more than 10. Okay, so we know, I guess it is drawing a chain of reasoning about it. But what I'm saying is we know that 10 or more will give you the wrong answer and we'll say game is over. And the game, so we won't ever go to slot 11 or 10 or 11 or 12 or whatever on that array. So I believe that's going to be sufficient. Now let's put one in. Let's make it work. Birdsong Hangman. Okay, so A, B, C, D, E, F, G, H, G, I, J, K, L. That's 8 if I'm counting right. M, N, O, P. Okay, there it is. All right, so we've made the game over check for too many wrong answers. Okay, now I think, well, let's get that. Now we're to print the game over, so that'd be good. Because it was a little, it was just kind of like, oh, you got a prompt again. All right, so maybe over here we'll print that. Okay, so print game over. Actually, we probably have the information to say you win or you lose. As well. So let's do that. Let's print like game over, you win. And game over, you lose, you know. Okay, so I think the information is there. I think it's really just display. Let's find game loop. So we're okay, so 600 we read the character and then we do the stuff and display. So if our character made the game over, we still are displaying it one last time before we detect that the game is over. So yeah. All right. So, but I think we can test. Well, I think there's a method. I think our display needs a method that part of the state is drawing the game state, you know. All right. So let's get that method, and it's gonna need you win and you lose to figure out what it wants to do. Okay, so let's see. So I guess we'll start with a test. It's kind of like game over, so let's do that. All right, so test game state empty if game not over. Okay, so equal. All right, so let's make an answer string to array, and then 2 wrong guesses. Repeat $. Okay, so empty answer set, empty wrong guess set, and then game state should put a string on the stack, and that string should be empty. Okay, so if you haven't guessed it right or wrong, then there. So I think that's game state, and then let's go ahead and put it here. Game state, string showing win, lost, or neither. Game state. All right. And then this is, let's just say game over. If it's over, we're going to do nothing. Do I have to worry about that? Well, let's do it the other way for now. Let's game over not. If the game is not over, well, let's make a wrong answer first. Okay. That'll surely. And this test will definitely fail. Okay, so they're just all screwed up because I've got 2 things. Well, the game is not over, so it's got 2 things on the stack, and it's just not good. Okay, but if the game is not over and we push an empty on the stack, well, actually, we don't even need to do that, do we? We can just push empty and make this test pass. All that stuff will come later. All right, but this is certainly easy. And I have to repeat this thing because they always rely on this stuff being compiled before them. So it's a, I don't know if it's a good limitation, but it's a limitation. Okay, assert equals string. Let's try that. Okay, good. All right. Yeah, now let's test game state win if you win. Okay, so answer oddly. Well, let's just simplify this. O. And then let's do clue. O. I guess that really comes first. This one goes away. Game state. And now I want to say you game over, you win. Okay, and this should fail with what we have. Yeah, I'm going to make you put the same contents but a different string. Or same position but a different string. Okay, good. Because we haven't done anything yet. All right, now if game state is game over, if it's true, then we have to do something else. We're going to push this and then phi. Okay. And let's just put our string, game over, you win. Okay. And then the other one should still be passing. Good. Oh, I didn't put my test name in there. Okay. Well, let's finish that, and then we'll clean these up. We're almost done. Okay, game state, lose if you lose. Wow. Okay, answer that. Well, I don't think we care about that. Olive. Answer olive. Okay, so the answer is olive, but you've got, let's make it 10 wrong guesses. Game state should be over, you lose. Okay. This test should fail. Okay. And now, so this is if you win, if, then we push that. Else, game over. Wow. Over, you lose. Okay. So I don't know if that's... It's enough to make you wish for a nested if else, that's for sure. True, but I think the reason I did it this way is because I want to make the display just called game state and show it where it wants it, and not have to do any logic in there. So I'm pulling display logic out, or logic that we would use in the display just to decide what to show. I'm pulling that out into this to make the decision. If the game is over and you win, you win. Otherwise, you lose. Otherwise, we're not ready to say anything. Okay, so let's make sure this works before I make too many claims. And then this again. And this should pass now. Okay. Good. Now we got some cleanup to do because I have apparently spaced how we write our tests. All right, so that was there before. This one was not. We want to put this dot $barrel. Actually, I kind of like spaces around these just to keep things. We didn't put them in a test calling method either, so we'll have to do that. Okay, now I think we put that one in. Test calling string to update. Yeah, okay. Well, did I put game over in there too? You can definitely see where the test framework, the lack of flexibility in that. I don't have a good way. I'm trying to think if there's a way to register my test with some other method or something. But where's... I thought I had a test for game over. Maybe we didn't have a specific explicit test. Okay, let's get these. Well, Get this down and test all. Kind of adding things as we go. Yeah. All right. Okay, so I think the last thing I want to do to that is I want to show this. So game state, wrong at, well, where it should go, I think, oh, I guess I got to look at the numbers. Title is line 2, scaffold is line 6. Okay, so the top line is 6. Let's say maybe 9 and 40. Draw at wrong guess is maybe 45. Game state is a string. Row 9, column 45, draw at. Okay, so let's save that. I'm going to do this from scratch. Okay, and then test Hangman. Okay, so A, B, C, D, E, F, G, I, J, K, L. Okay, maybe a couple more characters to the right. Yeah. And we're just doing this visually. No, I got to start it clean. Hard to replace one routine in the middle because all the other ones after it get invalidated. Test Hangman. All right. T-E-S-T, game over, you win. Yeah, I think that'll do. Now, the only reservation I have is this being up here. I think maybe display should... let's do... empty string 25 1 draw at. Okay, and I don't know, we're getting into the pretty stuff. Yeah, we could move things to the left if we needed to, but this Hangman. Yeah, that's going to be better. Yeah. All right. And the cursor's down towards the bottom. All right. And 25, I think, let's make it 24. Just this old terminal standard. 24 or 25 lines is sort of the standard terminal size. So we'll make sure it's toward the bottom, but that's okay. All right. Okay, so I think what I want to do is totally clean, build everything and tests, run the tests, make sure they're all still good. All right, just checking. Okay. And then the tests. Okay, that goes slow enough I can kind of read it. Test all, a bunch of stuff. Okay. Woo-hoo indeed. All right, so ACP, print, win or lose, message, win, game over. You know, we could do the play again thing, but I'm just not going to. Um, I know there's refreshing and stuff we would need to do. I mean, it would take us a while, and I don't think we'll learn anything doing it. I think it's just we got to make sure answer wrong guesses and clue get reinitialized properly, and anything else. Most of the other stuff holds things, but it's static information like the list of routines to call to draw stuff and all that. So I don't think there's any learning in it. I think because this will be our last session on this, I thought it would be good to look at the one that's on my mind. Let's see, we did this and this. Is that array thing, the array out of bounds check, that I think that would be kind of easy to do. And yeah, we should do that too. List of words and pick one randomly. I mean, we could spend another week on this fooling around with stuff, I'm sure, but get our 3D drawing stuff in place. I don't know. I would love a little beep if nothing else too, like uh, you know, beep out a Morse code of, SOS or something if you fail, victory if you succeed. But I think all that stuff would be just programming in the thing we've already been doing. So I don't think there's anything there. I think one last go into the array stuff and see if we can put that array bound check in. There's plenty of other things we talked about doing too, but okay, this stuff we've already dealt with all that. I guess I can put it down here, but this is really Hangman rules. Okay. And this was Hangman implementation. But yeah, these kind of things I think would be good. And then I want to take maybe 15 minutes or 20 minutes at the end and kind of walk through things, count the lines, just kind of take some basic statistics and just review what we've got. So the array thing, that feels like the most egregious, easy to fix thing. And actually the stack underflow is probably pretty easy too, but that would be fine. Debugging tools, stuff like that would be helpful, but yeah, I'm not gonna do it. Let's see, we did create a fill command. I mean, some of these are more environmental. But I think that'll just about fit in a good amount of time that we have left. 3:15, so 4:10, 4:15. Basically an hour to do that thing, and we'll give that a go. The other one that's on my mind is this relocatable addresses thing. Like, I really wanted to get that out of the code space and into the memory space, but I think you brought up this one before, and I think that it really is the more critical, more likely to catch problems kind of thing. This isn't a problem. It's just kind of an optimization. All right. Let's see. Well, I had my break. Maybe we'll go to like 3:45 and take a break then, if that's all right. Any complaints? We'll take it now if you feel like it, but that's good. All right. So we checked that in. So at this point, we can close Hangman and tests for now and get back into the mindset of the compiler. Well, somewhere there's array at. Is that variables? Array at. Okay. Yeah. All right. So here's array at. It pops index, pops the address, and then it pushes stuff there. And then array assign, the next one down, it's the same thing. But so the address Let's see. I'd have to look. Really, I don't remember. Is that the? That's the. What is that? Well, the way it's used, it must be the address of the array. Yeah, because okay, the array just loads its own address. Um, all right, so I think, yeah. So the problem would be we don't know the boundary of this index. We don't know what's like if you said create the array with 10 elements, we create those 10 elements and we throw away the number 10. We don't put it anywhere. And so my proposal would be put the 10 in front of the array and then make the pointer move down one for the address we're going to give out. Now I don't know where that, okay, array pop value. Okay, yeah, this is the one that's doing it. Okay, so data pop, number of cells, write that many zeros. And the standard epilogue always ends with a 0, I think, is why it's n-1. Or maybe BL variable. I don't know. We'll have to see. Is variable in here too? Yes. Okay. MetaWord takes the following name and, oh, it always starts with a 0 at the first address. Okay, so a variable just allocates 1 0 word. And load address. Load address. Well, load address, is that in here too? Yeah. Given the address of the secondary, push the following address. Okay, so I think we're going to do this refactoring split thing again. And I really should work up a good name for it, but in a way, I think of it as projection. Like you've got some structure and your tests project out and it makes a shadow like this. And if you change stuff inside, I don't know, I can't really do it this way, but it's projecting and it looks the same as a shadow on the wall, but the actual structure is different. If you project it from a different angle with different tests, you might be able to detect the difference in the shadow, but coming from the same angle, you get the same thing. Yeah, I'm gonna have to think on that one. It's definitely it's definitely something I picked up from like watching Kent Beck and others refactor, that kind of a thing they would do to create the room for the next thing. And I'm kind of willing to go fairly far. Like if it's mathematical, kind of like the logical thing where 0 or false is false, introducing that, multiply by 1, subtract 0, any of that kind of stuff is very normal for it. Okay, so what I'm going to do for this one is, right now, load address is used by variable and by array. Oh, shoot. Now, what's he doing? Right, because variable makes his header. Let's see what load address looks like. Okay. Add 8. Well, I don't know. It's going to be harder. I was thinking of either doing a load address and load array address, but variable does that. And variable is a word that gets called by people. And that's when you call var, you're calling this routine. Where to start? Well, I guess I could extract variable this could take an argument for this. All right, let's do that extract method kind of thing. So I'm going to say make passive word. Okay, and this thing read word and make passive word. Okay, the inputs, well, we don't really have one. Secondary space is implicit, I guess. I guess I could say that forward instead of backwards. Okay, so I'm just making it like it is now. I could add a size. Oh, yeah, that might be good. All right, let's get it extracted first, and then we'll play with it. All right, and then at the end he's going to do a return, and he's got to do this stuff because he fools with addresses. Okay. All right, so make a prologue, do this. Right, and this thing should then just be able to call make passive word. Because he's not modifying anything on its own, I think we can... No, we have to do this. I don't need to make another infinite loop happen when we already learned that. All right, because he does BL gets his return value based on things like you can't call a B. If you call a BL, you have to call standard epilogue or make the same thing happen. All right, so he does make passive word, and then this thing, BL variable, well, I think he can call BL make passive word, makes the header. Okay, that to me should be the same. Okay, so let's do a make. Should get no errors. Now, isn't that funny? The first time I ran that today, it was just like half a second. All right, that's not terrible. All right, we're looking for any red or anybody who failed. Okay, I'm not seeing anything. Okay, good. Okay. So add size 1 for variables. So are you thinking like we would treat variables as arrays of size 1? Is that kind of what you're saying? And that would make it the same across both. Actually, yeah, that might be the easiest. Okay, so right now he stores 0. Read word, read define word. Right. So if we did that, then load address would have to load 16 away. Because it would be past the word. But I don't think... I mean, basically this is costing us an extra word in our variable. It doesn't take any more time. Or at least I don't think adding 8 versus 16 is going to be a big deal. All right. Let's do that. Yeah, they both have reserved size. So, all right. So then the same routine does it. So I was going to make this a parameter, but really it's the size. So we're going to refactor this to take x0 equals size of array 1 for a simple variable. Right. Okay. And then the thing I always forget how to do, we need to make an extra array. We need to hold that parameter around. I know people do it. Here we go. Okay. And then load our SP pound 8. Okay, so back to variables. Make passive word. Store x28. Okay. And then load that. Loader x28. Oh, comes before the epilogue. Right. Yeah. Okay. All right. So now x0 is assumed to come in. Let's store x28 equals x0. Okay, and that's in that register, so the BLs can't overwrite that. They're required to save this if they change it, just like we are. Okay, so load address x0 load address. All right, so right now nobody's passing anything in to x0, but we don't do anything with it either. We write to it but never read it, and then at the end we restore this. Okay, so let's move x0 gets 1, and then this guy move x0. Oh, we don't even have to. We pop that number of cells into x0. Oh, we're going to have to do the same thing, though. We got to keep that thing around. Okay, so I want to get x0, but I need it after the call. So I'm going to move this up and then move x28 gets x0. And then I trust that will restore. Well, I don't have to do that. Let's just work with x28. Okay, and then down here we can just use it, I guess. Okay, now I'm not doing anything above yet. Yeah. Okay, so hopefully this is preserving this and using it correctly after that. Variable make passive word is not doing anything with x0, but it all should still work. Okay, so save and build. Store, I guess that's move. Where's my array? Data pop x28. Okay. All right. Good. Okay. So again, we've moved. I mean, this is all refactoring still. So we make variable and array allocation pass the requested size. Okay. All right. And then now, I think everything's in place. All right. So make passive word has x0. All right. Store x0. Okay, we're loading the load address routine and then storing that as the operative word. Okay. But I think what we're doing here is we're going to store secondary x0. No, x28. Okay, so this, the define word creates the pointer and all that, the word itself. Then load address is the, normally that's start2d for a secondary, but it's load address for a passive word. And now we're storing that load address in here. And normally we would only do the 0, store the actual 0 value for this thing. Now we're storing the size and then the value. Okay. And so if load address is going to get that, it's going to have to go up 1 to do it. Okay. Skip over size value. Okay. So that should put the extra stuff in there. The load address should, instead of grabbing the 0, now it would grab this, but we just made it go 16, so it's going to grab the 0 again. So that seems okay. Yeah, I think this is good. Shouldn't x28 be before the address? No, let me get a picture. Gosh, it's been a while since we looked at these now. Compile strings. Wait, a picture for arrays. Huh. Yeah, I never really did one. Okay, let's find. Gosh, we played with a lot of stuff. Okay, yeah, this. So the link, the make header stuff or whatever it was, took care of the link and the address. Well, basically when you create one, it writes the string name to the secondary memory, and then it writes the link, skips around the name, and then address of name points to the name, and then address of the code that we're going to interpret. Normally for secondaries, it's this thing that runs through the secondaries. But now, for a passive word like a variable or array, it's pointing into load address, it points to the load address routine that knows where it is, skips forward 8 to the next value. Now we're skipping forward 16 to skip past the size. Shouldn't X28 be before the address? Yeah, no, I don't think it should. It's the it's going to be the first thing in this pink area for a passive word. And maybe we should make a picture of that, because it's not really, well, actually maybe it's in our design notes. I don't know. Which is where I should have looked for before. Yeah, this would be a good place for that. Okay, so this is a passive word, var or array. Okay, and I'm not going to put this stuff in, but address of load address address of the name, load address, and then the size array, 1 for a var, and then the contents, array sub 0, array sub 1, array sub n minus 1. Okay, and then these pointers can go away. And then load address, let's see how it does it. Come on. Well, that's not a bad font size. Does that still fit? Okay, so passive word, yeah. And that's the difference. Yeah, the strings up there. We won't need it. Maybe I should bend this arrow the other way just to be. That's not really quite right either. I hate it when it grabs these things and won't let you just go somewhere. Well, that'll be close enough. All right. And then this, I'm going to move this pointer over because load address is right here. Okay. Yeah, so I think that's our change, that this always has it now. So I think that's a good picture. Okay, so he's skipping over. He puts in the extra word. Nobody's looking at it yet, but we're trying to make sure it's there. X0. Well, we need that X0 here. Move. X0 gets X28. Because passive word needs it. Needs the count. Okay, so variable sets it. This thing sets it. Okay, this thing is string allocation. Yeah, the array, they're all coming out of secondary space at this point. It's almost like it should be primary space because it's really where everything is. Boy, and you know this, I think this should move up there too, actually. Right now we store one thing, but we could just count and store all of them and then come back. So, but let's get this working first. Okay. So, again, I think we're good. I mean, well, I obviously can't do these things. Add x0. Wait a minute. Unexpected token. Oh, yeah. Too much 10th. All right. Oh, no. Load address pushes address of secondary. Oh, well, these may be correct in their complaint. Load address pushes address of secondary. Yeah, it is going to be, they do need adjusting. Okay, so let's, maybe let's put this back to 8. It's still going to break, but let's get the tests that justify it first. Okay, so load address pushes address of secondary. First one. Okay. Load address. Right. So the address we expect to get now is 16 off of X1. So that's the place we're loading from. Okay. So let's make sure that well, variable test should run almost last, so I guess I don't need to run it separate. Yeah, jumping between languages, yeah. Oh, there we go. Okay, load address pushes address of secondary. That did not come out right. Oh, yeah. I have to change it to make it pass. Okay, I'm going to have all these other broken still, but I think, okay, yeah, so that passes. We'll have to be careful. Okay, who's next? Variable writes header and value to secondary. Okay, well that should change. Okay. Secondary space was adjusted to the right boundary. That's a good test. First cell is the pointer to the old dictionary. Dictionary pointer is updated. Cell pointer is pointer to new string. Third cell points to load address. Fourth cell should point. It's not the initial value. Contains the count, which in our case we're making a variable, right? Yep. So this should be 1. And now the fourth cell, 24 plus 8 is 32. That should contain the initial value. Okay. Cool. Okay. Second assert fails. String was written to dictionary. Secondary space was adjusted to the right boundary. So 984, 976. Oh, this should be 16 bytes. Variable count 1 and initial value. 48, 6 times 8, 48. Okay. That seems okay now. And then the second to last. Ooh, that's the one. Oh, I said it should be a 1, but it should be a 0. Okay. Let's make dot. Variable test out. Okay, that's passing. Array kind of has the same problem. Okay, so at replaces assign starts. Array writes headers and values. Okay, so 3 times 8 bytes for header cells. How big do we make this array? 3. Okay, so I think this should go up by 8. 3 times 8 bytes for the header cells. Yeah, that's separate. 3 times 8 bytes for the count. And 3 times 8 bytes. Okay. And then the third from last. 4th cell. Okay, yeah, this one should be the count. Count 3. Value for array sub 0 equals 0. Goes there. Okay. Make. Okay. So, load address now skips past count before loading. All right. Well, that's a good place to be. We're not done, but what we've done now is we've set everything up to be there. We've got variables and arrays. Before they allocate their actual space, they allocate the count. And the thing that finds their address skips over the count. So that part's good. We just don't enforce the array access being in bounds. All right, so let's take a break. You got a counter. Are you talking about the count in the cell now? Yeah, we have that information. So we have enough stuff at runtime. We could go look at that variable address we get back -8 is going to be the address of the count. And we can do an assertion before we call anything. So let's take a break. We'll come back and do that. And then we'll do a little summary. And I think that'll take care of us. All right, so 3 or 4 minutes. All right, welcome back. Okay, so we have, I think everything is here. And even our runtime, I don't think it should matter. Let's go back to array at. Okay, oops, I want this one. Array at. Okay, so yeah, the deal is x2 is the variable address. So I think we can make, well, I think we can demonstrate with a test that what we want to happen is not happening. And I think we'll do a version 1 and a version 2 real quick. Version 1 is like, you're out of range, we're going to force you to 0. Version 2 is, we're going to call some routine and blow up on you. And we already have a mechanism to call a routine. We'll do something similar to that and print, some array out of bounds kind of thing. I don't know if we can find, I bet we can find the name. Wouldn't that be cool? Because we know the address of the array and go backwards the right number of words, and you're to that pointer to the name. So we can get to that. All right. Cool. So let's do a variable test. Array at replaces variable and index with value. Okay, that's a good starter test. Wow, lat variable. Oh, I didn't change the comment here. Okay. Lat variable has 42. Oh, maybe I've got the wrong. Array at replaces variable and index with value. Okay. Array at too low. Axis is x1, x0. Array at index too low. All right, so x0 is 999. Push that. Okay. I guess I got to understand what array at does. That's at plus a equals mem of b sub a. I'm a little puzzled here then. We push 999. Oh, that's our stack check we're doing here too. Okay. Push the variable, the array address. Let's push a -1 -1 array at, and then this should be, I think it was 42. Yeah. 42. Out of range array sub 0. Okay. This test will fail, I think. Could well blow up with a memory problem. Yeah, this is passing in a negative index. True, but I think there's a nice little trick. If you compare unsigned with something that's bounded by 0 on the bottom, If it's negative, it looks like a very big number, and so it'll still look too big. So you kind of catch it for free with the same test, but I'll do two separate tests. Okay, so that failed. We got who knows what instead of 42. Can we tell what was there? L at address. Where are you? P2 line 3. Yeah, I could put quad. What's our number? 7. No. 7171335. Our lilies. Maybe I'll put. Okay. So this is not changing anything. It's just going to change that the test is going to get that instead. Yeah, we could define it to read from the end. It wouldn't be a bad decision, but it would take longer than I want to give it today. But I mean, like, Python and lots of languages do that. Negative indexes get you -1, get you the last item, and -2 the next to last, and so on. Very handy. All right, so here we are, 7173500. Okay, so this is failing. I'm going to make the same test with one that's too big. Oh, this is array at. Okay, okay. So, well, we have to set that size up more correctly then, don't we? Okay, this is the value before. It has to be the size, not just lilies. Okay, so this is 3 words, size of array. Okay. Whoops. All right. Index 0, index 0. Too big. Axis is index 0. Okay. So let's do 4. Well, let's do 500. Okay, maybe we can even crash it if we do it hard enough. Okay, and so yeah, out of range to that. Okay, I'd like it to fail dramatically, I guess. But if I don't put this in the test, it's not going to fail at all. Okay. Well, I did it again. Okay, yeah, they both fail. He grabbed some random 0 out there. Could be anywhere, kind of thing. All right. So now we can talk about this thing. Okay, so array at is the thing we're testing. So we're going to take x1 is the index. Well, we're going to have to get the size. x3 gets, no, let's do a subtract. Can I do that in one go? Well, let's do it the easy way. Move subtract x3 equals x2 minus 8. Okay. And then load address x3, contents of x3. Okay, so now x3 is the count. And I got to look at the, we haven't busted this out for a while. Maybe I've got it in my environment one. Open with external. Yeah, this is the table I want. Okay, not equal. See, we want unsigned higher. Yeah, so we want to use this one. So if the number is higher than the bounds, actually it's unsigned. Oh, that's tricky. We don't have an unsigned greater than or equal. Well, actually, unsigned lower or the same is probably good enough for us. Okay, so we're going to compare wherever it got to. We're going to compare x1 to x3. And if it's less than or equal, well, no, we want less than. Really, there's no unsigned less than. Unsigned lower or same, unsigned higher. That's the only ones. Okay. I guess we'll subtract one from the count. X3 gets x3 minus 1. Oops. Okay. Right. So that's the maximum you can be. And so if you compare branch, was it LS? Okay. L access array, which is the old thing we're doing. Okay. And then otherwise, we're going to set the index to 0. That's the index. Okay. So I guess I could say count precedes array. And then we'll load the count. So if you have 3 things in the array, you can only do 0, 1, or 2. So it's less than or equal to 2. Okay, that's why I subtract 1. Okay. Otherwise, we're changing your index to 0. And then we go to access it. We have the implicit multiply and all that stuff. Okay, so I hope I've done this right. Let's get back to our here. So my hope is those 2 tests pass and nothing else blows up. Okay, well, let's see what I did. I have to remember load address. Load address is, oh, this is load R. Load address gets a variable in a memory address, but load R can take the address of an address. Larger will also be 0. Yeah, you can't go negative, but anything larger. So -1 is really looks like, you know, -1 in binary is all ones. So it look on an unsigned level, it looks like this huge, the largest possible number. And so that is guaranteed to be bigger than 0. So that's why this kind of works. I don't know if it works with, I guess one's complement makes its zeros have a high bit set. So yeah, same thing. Okay. What am I doing wrong? Kind of hard to know. That part's funny. Have I done this twice? I don't think so. Okay, let's try this again. LXS array, you gotta put a colon. All right. It could, but really, I'm gonna make it call a routine. No, I'm not. If I were taking the next step, I would make it call a routine, right? That we did stuff like that. Oh, well, I don't know where we put those routines. Interpreter maybe. Word not found. Okay, we have this defined routine. Yeah, there's that in the defines. Word not found. REPL macros. Okay. Yeah, so there's global word not found handler, wherever that got off to. Okay, so if we did like this, we've got the global word not found handler. And we did a little bit of indirection so we could call it. We could put our own routines in for our tests. But we don't have, this is just for word not found. We don't have one that's for other problems. Okay. So really, what I would prefer to do would be like make an array of these pointers to error handlers and do kind of an indirect call on those. And then we could substitute the error handlers. But gosh, this is a very old technique. It's almost like the old days technique before you had C's virtual addresses, where they, you know, you call in and it calls in directly to the thing. This thing, like old libraries, I mean, like from the 70s, kind of old, would have this set of pointers to the functions that you really wanted to call, and you call them in directly, kind of like we're doing for our handlers. And so I would do something like that, have this array, and then somewhere there's a pointer to the array. Yeah, jump table kind of thing, but a pointer to this jump table that knows that offset 0 is the word not found, and offset whatever is array out of bounds and stuff like that. So I would the next step would be to do that, and make a global word or array access out of bounds handler, and instead of shoving that x0 index in, I would call that. And I didn't want to do that in the first step because this it just required more mechanism to set up, and I don't want to just call it. I'd want to make it testable, so I'd have to be able to. It had to be like this, that it's global, but I can replace it, and all that kind of stuff. It would be another half hour, I guess. That's the bottom line of it. And I wanted to save the last 15 minutes to just kind of go over some things and catch some statistics and look at any highlights or something. So, but let's run this thing and make sure it's doing what we think it should do. So I'm going to take, I'm going to make an array of 10, array foo. And then if I do, man, I cannot remember the order for these things. The address index is on top. Okay. Yeah. So if I do foo 3 at, I should get 0. No. Is it the other way around? Yeah. Okay. If I do 0 array, oh man, I don't remember these things. Mem sub c sub b equals a. Yeah, 0 array 77 at plus equals. No. Well, do we do it in Hangman? Okay, let's pull him in. Okay, he does stuff with arrays, so if we do game Hangman, okay, so 77 0 array at plus equal. Okay, let's try that way. 77 0. It was, I think it was c sub b equals a, right? Mem sub c sub b equals a. Okay, so 77 is the value. 0 foo at plus equals. Oh, golly. 10 array foo. 0 foo at dot pop. 77 0 array. No, foo at plus equals. Now we did not change at plus equals, so I'm doing something wrong with it. B sub C, C sub B. No, that's totally backwards, isn't it? 10 array foo. So C sub B equals A, I think, at plus equals. Okay, dot. Oh, dot should be lilies, but foo 0 at, no. 0 foo at plus, no, I'm doing backwards again. Okay, 10 array foo. That part's good. Foo 0, 77 at plus equals as assigned. Now foo 0 at plus dot should be 77. Okay, now foo 100 at plus dot should be 77. Okay. All right. Yeah. So I think it's using a sub 0. It's an interim step. And again, if we were spending, another week on this or whatever, I would certainly take that next half hour and put the global error handling in, and then probably move to the jump table and then do some other things. But I would say we did this. I think we can call a global handler as a future thing. I don't anticipate coming back to this, but if we did, and this is really kind of our runtime, substitutes index 0 for out of bound value. Okay, so I think that's all right. Good. Now I'm just going to touch. Let's see. Well, what do we have it open still? Environment notes. No, I want the other one. Design notes. Okay, so I think the fundamental thing in sort of this indirect threaded code, we have two pieces. We have the dictionary of primaries, which are the hand-coded assembly language coded routines we created. And they have this standard header structure, a link to the previous dictionary entry, followed by the pointer to the name of the routine, which is stored in secondary space, or in wherever the dictionary is, but it's stored outside the range somewhere. And then points to the address of the assembly code. And so our dictionary looks like that. And you search for something, you just kind of work your way back. Offset 8 is the name of the routine. Do we match that one? No, let's go to the next one. All right. The secondaries, they fit into the same dictionary structure, although they're allocated in a different block of memory. And they also have that link to the pointer and the pointer to the name. And then they don't point to arbitrary code. They point to start2d always for these kind of secondaries. And start2d is expecting the rest of the body to be a list of addresses. And those addresses are the addresses of the code. And so it's going to look up those previous ones and substitute in that address into this. So at runtime, this is why we have to recompile everything from if we change a routine in the middle, we have to recompile everything from there down. This is why, because we're not storing a pointer to the dictionary entry, we're storing a pointer to the actual code. And so it's a runtime trade-off that at runtime, we don't have to do this kind of double indirect thing. We've done that at compile time. It's a decision. We could have gone the other way and said, oh, go look it up. You see a reference to a name. We could have put the list of pointers to the names and then make you go look them up in the dictionary. It's all this kind of trade-off. If we had pointed to this address, well, that might not be right. If we have a newer definition of the same function, like if we changed it, this address is going to be outdated. We'd have to go by the name instead. And so to avoid that runtime hit of looking things up by their name and then scanning through the dictionary, we've substituted the actual address of the code. And, for incremental purposes, it's not so handy. For faster running, it's better this way. All right. And then we have the passive routines today. They still look like a routine as far as how they fit in the dictionary, but their contents is not a list of addresses. It's a bunch of data. And so we've got a special load address that actually digs through and knows to find the data down here. And we changed that today. And I think everything else kind of follows from that. Pieces of the compiler, I'm not sure that's too good. It's there, but we talked through the dictionary. We know there's a data stack. There's a system stack for controls. Oh, the system stack is the procedure call stack, and then the control stack for if and else. Do I keep those? Yeah, I might pull those notes in for those. Oh, here they are. Okay. So yeah, compiling if and else, we have these low-level statements, if, true, and jump, and we basically build all our control structures out of those. And they're encoding direct addresses, so they're not doing any kind of compiler work at runtime. They just know, hey, jump to exactly this address. Okay. We could have done a relative address, dump forward 10 steps or whatever, but this saves you a little work not having to calculate that. In reality for this, an M1 Mac running at speeds they run at, the extra addition is just hardly going to be worth anything. If you do any IO, you've outpaced that by a million. Okay. Then the last thing I wanted to do is just let's check out sizes. Okay, and I'll keep track of this. Okay, so all our files, we got a bunch. All right, but we got the files. Let's do word count star tests dot s. Okay, so these are our assembly language tests. And okay, so this is lines, words, and characters. Okay, so 3,400 lines. Yeah, that's good. Interesting anyway. And then let's word count all our assembly code. Okay. Well, that includes the tests and the regular. So if I subtract 5,800 minus 3,400, that's 2,400. So we have a little more testing code than we do the actual non-testing code here. That's not unusual for tester and development, but that's okay. Now, most of these lines, some of them are macros, so they define some stuff. Oh, we should look at those too. wcount star macro. Okay, 276 lines of macros. Those code, that code, most of those are production. There's one for tests and one for AS unit, but they're not big. Okay. And so I think that's realistic. I mean, that's like you say, it's normal to be more lines of test code. Every if you got to test twice, so it's going to be bigger. There's going to be if statements. And while loops, you have to test at least 1 or 2 or 3. Okay, let's look at our Hangman code. Start at 10. What? Have I lost it? Didn't I call it hangman.10? Did I blast it? Oh, it's the directory structure. I ended up with that in there. Okay. ls minus l 10th. Oh, sorry. wcount 10th / star. Right. So Hangman has 640 lines. Tests has, I'm not sure. Let's look at test.10. Okay, that is more junky. Okay. All right. So here our tests are actually smaller than our Hangman. So that's kind of unusual. But that's what it is. Yeah. I don't know why. Well, there aren't very many ifs, relatively speaking. I mean, this is not a huge problem. I guess there's relatively more straight code. And maybe the fact that you have to do so much swapping around with the stack to get the right things on top. I don't know. It would be something to look at, investigate. All right, and then the last thing I want to look at is this. OBJ dump. Do I have that in here? No. OBJ dump, I think it was -d. REPL.out. Okay. Now, I've lost my calculator. But the start of this, I think it's 100,030. No, 100. Okay, so 100,222. How many twos is it? 3 twos. 2, 2, 2, 0. That's a. And then the last one is 3FA0. Okay, so let me get my calculator. I don't know why that got shut off, lost at some point. Okay, but let's take 3FA0 minus 2220 and then change that to base 10. 7,500 in 7,500 instructions basically. So yeah, not huge. Okay, now if we ls minus l REPL.out, it's much bigger because we allocated like 200,000 bytes of whatever. I mean, it looks big, but if you just look at the code, everything's in REPL.out. And even this, we put our dictionaries still in memory. Let's see if I can find it. Well, I don't know. This looks very suspiciously boring. Global word not found handler. I don't know if that's dictionary stuff, but it's from macros probably. I don't know if we can tell in here. Stubs. No, if that's something else. Yeah, I don't know if those. Well, these routines are small. And it's 4 bytes per instruction. 4, 8, 16. Sorry, 4, 8, 12, 16, 20. Okay. But I don't know if that pattern of global word error handler or something. This must be the dictionary stuff. The start. They're pointing off somewhere else. Yeah, I don't know, but there's something for the macros for creating our dictionary. Yeah, the allocation's probably too high. I mean, realistically, I just didn't want to deal with debugging it this week. Also, in a real application, I would have to do some sort of cleanup on the strings that got used but no longer needed kind of thing. I think we could mostly keep track of it because we can tell when you've got a pointer to it. Probably a reference count for strings would be enough. And then you got to worry about, compacting or something like that. But it would be manageable. I mean, it would be a thing, no worse than Halleck and Malak and Realek and all those. Okay, but I mean, so 7,500 words, if that's basically more or less the count, it's sort of like reflects this thing of, kind of being constant across languages, this the work to create array is a lot lower in Swift or C. In C, it's really just put your brackets and your index and you're good. Not even a line. Here it's 10 or 12 instructions. So definitely get a fair bit of that. But anyway, it's been very fun for me to play with assembly language again in my life, and I was happy to learn some ARM64 stuff. I don't anticipate doing a lot more assembly, but I've always wanted to try this indirect threaded code implementation, so it was great to be able to try that. And thanks Mudshark666 in particular. You've been here through the whole project, and one or two others that have been following pretty regularly. But it's been good. I think the Hangman was a good suggestion for the game to do to demonstrate that we had an actual implementation. And what I'm anticipating doing next, I'll just very briefly. Yeah, I even have it open already. I'm calling it Fume for River and FI for Finance. I want to make an app. It's going to track pools and streams of money over time. And I'm going to switch back to Swift. I want to learn observable. We've been using at at binding and at observable object, and this observable is their more modern one from the last year or two, and then Swift data for persistence. I don't see going back to Java. Um, I might consider doing a Kotlin one over at some point. I really think of Kotlin as a better Java. I'm really rusty on that too at this point because it's been several years, but um, I don't know, 3 years, maybe 2 years. It's hard to tell with a pandemic. But anyway, I anticipate doing this. I'll be back a week from Thursday, which is May 9th, if I'm thinking right. And we'll take a go at this. I don't know how we're going to do it. Just a quick glance at what the idea is, but you're going to have these baseline things about like what's your income or what's your savings or things like that. And then I want to be able to plop scenarios on top, like what if I retire at age 62 or 67 or 70? And what if my wife does the same? And what if the economy collapses, or whatever these scenarios I want to invent. But I'd like to be able to do some of that. And then also sometimes I'd like to be able to match up and say, you know, maybe my living expenses are going to be covered by my savings. And if I take, like, clearly, if I take 3,500 a month out of this, it's not going to last long, you know? So figure out those problems like that. So that's where we'll pick up a week from Thursday. Once again, thank you so much for the chance to work on this assembly language project. I know it's a little out of the normal range for most projects and most things, but it was worth doing. All right, take care. Have a good weekend. Next week, Thursday, 2 to 4:30 Eastern or 6 to 8:30 p.m. UTC. All right, bye-bye.